Let's take a look at this VJC 2021 paper 2, and we are going to focus specifically on the statistics part. So let's jump directly to section B. And I have to admit that when I was trying out this paper, this statistics is actually not as easy. So we're going to be having an interesting time because we are going to be working on a slightly more challenging set of statistics question from this VJC 2021 paper 2. The first statistics question is question number 5, and we are going to be working on these word misspellings. And there are 12 letters inside here, and looking at these 12 letters, they are going to be identical objects. They are identical I's, identical S's, and identical L's. So let's try to rearrange these 12 objects so that we can have a better overview of all the identical objects. So let me rewrite this word misspellings. M-I-S-S-P-E-L-L-I-N-G-S. So this word misspellings. And the first thing that we want to do according to what the question wants, is to have both I's placed in the beginning and both L's placed at the end. So part 1, the scenario is like this. Both I's are supposed to be placed in the beginning and both L's are supposed to be placed at the end. And in between there will be 1, 2, 3, 4, 5, 6, 7, 8 other letters. So if I were to be arranging these 8 letters, it is going to be 8 factorial. And within these 8 letters, there are actually 3 identical objects. There are 3 identical S's. So I'm going to divide this by 3 factorial. And my answer here is 6720. This is part 1. And let's take a look at part 2. In part 2, we are supposed to find the number of ways that these 12 letters can be arranged such that between any 2 S's, there must be at least 4 other letters. So if you think about it, how many non-S's am I going to be working on? I have 1, 2, 3, 4, 5, 6, 7, 8, 9 non-S's. So in order for me to make sure that there are at least 4 letters between the 3 S's, it will be either 4 or 5, correct? I mean, if I were to be having 9 non-S's, no matter how I try to break them up to be slotted between the 3 S's, it should be 4, 5, 4, 5, or 4, 4. So we will have just a few cases to be working on. Let me try to list down the first case. The first case that we can probably imagine together is when there are 4 and 4 letters between the 3 S's at the same time. So for example, if I have S, then 1, 2, 3, 4, then S, 1, 2, 3, 4, then S. And I'm going to make sure that this operates as a unit by itself. So I'm going to group this into an object. And the reason why I'm doing so is because there are actually 9 non-S's, correct? But we have only used up 8 of them, which means that there will be 1 other letter. So if I were to calculate for the number of ways that this can happen, it will be out of 9 letters, we are going to be choosing 4 of them to be between the 2 S's, the first 2 S's. And for these 4 letters, we will be arranging them, so multiply by 4 factorial. And we will have 5 more, and for these 5, we will also choose 4 to be between the 2 S's, the next 2 S's. And arranging them, it is going to be another 2 factorial. This is going to be within this object, and treating this as an object, this will be another object, so we can permutate them, so this is going to be another 2 factorial. But let's not forget, for the non-S's, there are 2 I's and 2 L's. So I'm going to be dividing this by 2 factorial for the 2 I's and another 2 factorial for the 2 L's. This will give me a 1814440. Let me list down another 2 cases, okay, then we will calculate them after that. So the other 2 cases, according to what we have just discussed, it is going to be S, 1, 2, 3, 4, S, 1, 2, 3, 4, 5, then S. Do we have anything that is outside this object? No. Okay, because we have already utilized all the 9 non-S's. So for this case, out of 9, we are going to choose 4 for here. So 9 choose 4, 4 factorial. And we have 5 left, and we're going to choose all of them. 5 choose 5, then multiply by a 5 factorial. And for these 9 letters, similarly, there will be 2 i's and 2 l's. So I will divide this by 2 factorial for the 2 i's, another 2 factorial for the 2 l's. This will be 90720. Okay, I realize I've already proceeded doing the calculation. So let me write down the last case. The last case, it is actually very simple to this, very similar to this. It is just S, letter, 1, 2, 3, 4, 5, S, 1, 2, 3, 4. Then S. So it is going to be out of 9, we will choose 5 for this, multiply by 5 factorial. 4 left, we will choose all 4 for this, multiply by 4 factorial, and 2 i's, 2 l's are going to be how I take care of them by dividing by 2 factorial. 2 factorial, this is actually exactly the same as this, so we have a 90720. So the total number of ways that we are working on for Part 2 will be 181440 plus 90720 plus another 90720. So my answer here is going to be equal to 36280. This is Part 2. Let's move on to the last part. For the last part, we will have a group of 8 letters that is going to be randomly selected from the letter misspelling. So it's going to be similarly from here. We want to find the probability that it just so happened that all these 8 letters, they are distinct. All these 8 letters, they are distinct. How many distinct letters do I have from these 12 letters? 1, 2, 3, 4, 5, 6, 7, 8. So we happen to have 8 letters that are all going to be distinct from this word misspellings. So we are just going to be using up M-I-S-P-E-L-I-L-N-G. Okay, we are just going to be using up this over here. So if you think about it, what is the probability that we are going to be having a word that is formed in this way? M-I-S-P-E-L-N-G. So what is the probability of this happening? M. The probability of M happening will be 1 out of 12. M happening as the first letter, okay, it will be 1 out of 12. Then what about I? What is the chances of I being the second letter? I being the second letter will be, there are 2 I's here, so it is going to be 2 out of 11, okay, because there are going to be 11 letters left. Then it will, if I were to look at S, it will be 3 out of 10, because I will have 10 letters left after I've chosen the first 2 letters. Then P, it is going to be 1 out of 9. And E, it is also going to be 1, so 1 out of 8. And for L is going to be 2 out of 7. And for N is going to be 1 out of 6. And as for G, it is going to be 1 out of 5. So if I were to multiply all this together, this times this times this, if I were to be multiplying all this together, it is going to give me the probability of me getting this word M-I-S-P-E-L-N-G. But we know that this question doesn't just want this word. This question also wants other permutation of this word. So for all the rest of the other permutations, they're actually going to be getting us exactly the same probability as this. So now it boils down to how many times this is going to happen. And it is going to happen 8 factorial number of times. We're actually permutating this. So this will get me my final answer for this last part here. It is equal to 4/165. So this is question number 5. Let's move on. Let's take a look at question number 6. So in question number 6, we are looking at a scientist working on this raccoon, Alex. So there are n boxes that is placed in the room, and exactly one of them will be containing food. So Alex the raccoon will be opening up randomly the boxes to check whether there's any food. It will stop only when he managed to find food, and whichever boxes that Alex has already opened. Alex is trained so that it will not open that box anymore. And we are going to be letting X be the number of boxes that Alex opens. Okay, so Alex will be opening until when it finds food. And in part 1, let's take a look at what is going to happen in part 1. In part 1, n is equal to 3, so there are going to be 3 boxes. Okay, according to what the question says, there are n number of boxes. So we are looking at 3 boxes. We want to determine the probability distribution for X. So we want to list down the probabilities for all the possible cases. That's what the question wants, probability distribution for X. We want the overview of all the possible probabilities, which means that X can be equal to, because X is the number of boxes that Alex will open until when he finds food, right? So X can be equal to 1, since there are 3 boxes. X can also be 2, X can also be 3, and that's all. So we are talking about probability that X is equal to 1, probability that X is equal to 2, and probability that X is equal to 3. So if probability that X is equal to 1, which means that the very first box that Alex the raccoon opens, it is going to find food. So if this is so, what is the chances of this happening? It is 1 out of 3, correct? Because out of the 3 boxes, only 1 of them will have food. And what is the probability that X is equal to 2? For this to happen, the first box that Alex opens, it shouldn't have any food. So it is going to be 2 out of 3. But the second box that Alex opened will have food. So for the second box that Alex will open, there are actually just 2 boxes left. One of them will have food, which means that for the probability of the second box having food is just 1 out of 2. And this is also equal to 1 over 3. So it's actually the same as Alex opening the first box, and it found food inside. And the last case is when X is equal to 3. So the first box, Alex shouldn't find food. For the second box, Alex will also not find food. 1 out of 2 of them have food. So for the second one not to have food, it is going to be 1 out of 2. And for the last one to have food, it is going to be 1 out of 1. Because, I mean, if for the first 2 there's no food, the food must be in the last box. So the chances is 1, or 1 out of 1. And this will be cancelled. It will also be 1 out of 3. This is already the probability distribution that is asked by the question, because we just need to quote all the probabilities of all the possible cases. But we can definitely build for ourselves a probability distribution table, something that we probably are a little bit more familiar with. So it is going to be this: X is equal to X. So when X is equal to 1, we have a 1 over 3. When X is equal to 2, we have a 1 over 3. And when X is equal to 3, we have another 1 over 3. I think part 2 is a little bit ambiguous, okay, or rather it can be a little bit misleading. But what part 2 is asking for us to state the expectation and the variance, right? For part 2, we are supposed to be working on n again, okay? So we need to ignore this 3 over here. I think it would have been a little bit clearer if the question were to specify once again, or to just verify that we are working on a general number of boxes again, so n boxes. So we are trying to find the expectation of this case, expectation of X, when I'm working on n number of boxes. So let's try to make use of our experience in part 1, and we are going to try to quote the probability distribution for part 2. And if you think about it, right, most likely even for part 2, the probabilities are going to be the same. My suspicion is that since this is 1 out of 3 boxes, 1 out of 3, 1 out of 3, so my suspicion is that for this, all the probabilities are 1 out of n. But let's verify. Okay, let's do a quick verification. So if there were to be n boxes, what is the probability that Alex is going to find food in the first box? So 1 out of n number of boxes will have food. So the probability here is 1 over n. Okay, I think this is easy. For the second box, for the second case, we are going to be looking at when Alex finds food only in the second box. So for the first box, no food. What is the probability? N minus 1 over n, correct? because one of the boxes will have food. So the number of boxes that will have no food will be n minus 1 number of boxes. So n minus 1 divided by n, that will make sure that we are looking at the probability that the first box is no food, and for the second box there should be food. So for the second box to have food, it is 1 over the number of boxes left for Alex to choose will be n minus 1 number of boxes, because the first box has already been opened. This and this can be cancelled. It is going to be 1 over n. We are experiencing the same thing as here, right? See, 2 and 2 can be cancelled. Let's see whether this is true for probability that x is equal to 3. The first box, there is no food. The second box, there's also not going to be food. Right? We will have just n minus 1 number of boxes to choose from, and in this n minus 1 number of boxes, one of them will have food, so the number of boxes that will have no food will be n minus 2. And the last box, the box number 3, will have food. So it's just going to be 1 out of the number of boxes left, n minus 2 number of boxes left. So we can cancel, 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 cancel. And we're going to be having, once again, a 1 over n. And again, we're experiencing something that is almost similar to this. So from here, we can sort of like see the pattern. All the probabilities are going to be equal to 1 over n. So just like what we have done here, maybe it is wise for us to just build for ourselves a probability distribution table, since we are more familiar with working on expectation and variance based on the probability distribution table. So we have x here, and here I'm going to write probability that x is equal to x. When it is 1, when x is equal to 1, the probability is 1 over n. When x is equal to 2, the probability is also 1 over n. When x is equal to 3, the probability is 1 over n. How many boxes can Alex the raccoon open? It can open n number of boxes before it finds food. So the very last one will be n, and the probability is still going to be 1 over n. So based on this, let's try to find the expectation. The expectation is sum of order x multiplied by the corresponding probability. So it's going to be equal to 1 multiplied by 1 over n plus 2 multiplied by 1 over n plus 3 multiplied by 1 over n, all the way until n multiplied by 1 over n. And 1 over n is in common from term to term. We can factorize this out, which will leave us with a 1 plus 2 plus 3 all the way until n. So we have a sum of an AP. Sum of an AP with the first term as 1, the last term is n, and the common difference is 1. The number of terms that is involved is 1, 2, 3, 4, 5, n number of terms. So this is going to be 1 over n, applying sum of AP formula. The number of terms is n divided by 2, the first term plus the last term. So n and n can be cancelled. This expectation is going to be equal to 1 plus n divided by 2, the expectation of x. Let's base on this distribution table that we have just come up with, and we are going to try to find the expectation of x squared. Why are we doing so? Because we are going to be working on the variance, right? So if we were to be using the formula that we have learned before to find variance, we need the expectation of x squared. So let's try finding the expectation of x squared. It is going to be summation of x squared multiplied by the corresponding probability of x, which is going to be equated to x. So this is going to be equal to 1 square times 1 over n. So 1 square 1 over n plus 2 square 1 over n plus 3 square of 1 over n, and plus all the way until the very last one is going to be n square times 1 over n. Okay, I'm running out of space here, so it is this. And again, the probability remain the same, 1 over n, 1 over n, 1 over n. So I'm going to factorize out this. So we have a 1 over n, we have a 1 square plus 2 square plus 3 square plus all the way until n square. And we can see a hint that is given to us by the question on evaluating this, because the question gave me this summation of r squared from 1 all the way until n. So I'm going to make use of that. Let me try to re-express this here. This, if I were to re-express, it is basically just sum from r starting to 1, from 1 all the way until n of r squared, correct? Because when r is equal to 1, we have 1 square, r is equal to 2, we have 2 square, and all the way until when r is equal to n, we have n square. So this is going to be equal to 1 over n, making use of the formula that is given to us by the question. This is going to be n plus 1, 2n plus 1. This is going to be divided by 6. So n can be cancelled. This is equal to n plus 1, 2n plus 1 divided by 6. And based on this, now we can find the variance. The variance of x is going to be the expectation of x squared minus away the expectation of x squared. So this is going to be equal to this that we have here. It is going to be equal to n plus 1. And we have a 2n plus 1 divided by 6 minus away expectation of x squared. So minus away this square. So we have a 1 plus n square over 2 square, which is 4. And we are supposed to express this such that it looks like the expression that is given to us with a denominator 12. So let's try to find a common denominator of this, which is actually also 12. So this can be rewritten as 2 times of n plus 1 and 2n plus 1. This over 12. Minus away 3. Let me rewrite this as n plus 1. Okay, so n plus 1 times n plus 1 square over 12. So now we can factorize out this n plus 1 over 12. Okay, n plus 1 over 12, n plus 1 over 12, which will then leave me with a 2 times of 2n plus 1 minus away 3 times of n plus 1. So this is n plus 1 divided by 12. And what we have here is a 4n minus 3n, which is n. Then we have a 2 minus 3, which is minus 1. And this is actually what the question wants us to show. Question number 6. Okay, I think 6 is not as easy, especially when they require us to do a bit of inference here, a bit of deduction, not, because we are not going to be calculating every single one of them. So we're going to be looking at this based from the perspective of series and sequences, where we pick up the skill on learning how we can recognize pattern. Anyway, let's move on to question number 7. Okay, let's take a look at this question together. In question number 7, we are given 3 events, A, B, C. Probability of A is given. Okay, let me just write down the information here. So question number 7, probability of A is given to us as 0.8. The probability of B, this is given to us as 0.4. And the probability of C is, okay, C is unknown, and the probability of A union B, this is equal to 0.95. So part 1. Part 1, let's try to find A intersect B. I think this is, okay, this is pretty easy. We're going to make use of this, right? So since we are given that the probability of A union B is equal to 0.95, and A union B is also A plus B minus A intersect B. This is equal to 0.95. Probability of A is 0.8. Probability of B is given to us as this. This is what we are supposed to be finding, and it is equal to now 0.95. So from here, we can find what is probability of A intersect B, and this is equal to 0.25. And we are supposed to do a check to check whether A and B are independent. So to check whether they are independent, let's take the probability of A, multiply it to the probability of B. Because if they were to be independent, then the answer that I'm going to be expecting here should be equal to 0.25. So let's do a quick check. This is going to be equal to 0.8 probability of A multiplied by the probability of B. And this is equal to 0.32. It is not the same as probability of A intersects B. So our conclusion for this is A and B, they are not independent. Part 2. Part 2, we are supposed to state the range of values of C, which necessarily implies that A and C are not going to be mutually exclusive. For A and C to be not mutually exclusive, we can actually express that on a Venn diagram. So if A is here, then C cannot be touching A. Okay, C cannot be touching A. So we are going to try to look at the conditions such that this will not happen. We are trying to look at a situation where A and C cannot be mutually exclusive. So what we are going to do is, since this is going to be representing the probability for A, let's try to look at the probability of A prime. That means we look at the space. Okay, when we draw Venn diagram, our idea is to try to look at the area in the Venn diagram, or the space that is in the Venn diagram, to represent the probability. So let's look at the space that is outside A. And the space that is outside A is 1 minus probability of A. So it's going to be 1 minus 0.8. This is equal to 0.2. So the space that is outside, this space here is 0.2. Which means that if this space can house the entire C, then it is possible for A and C to be totally not overlapping, correct? So in order for this not to happen, okay, in order for the case where A and C are not going to be overlapping each other, in order for us to prevent this from happening, can you see that C should be strictly bigger than 0.2, correct? It must be strictly bigger than. It cannot be even equal to 0.2, because if C is equal to 0.2, it is also possible that they are, if C is equal to 0.2, then it is still possible that they will not be, they will not be intersecting, okay? And we want to make sure that this will never happen. So by making sure that the area of C, which is the probability of C, is strictly bigger than 0.2, no matter how I'm going to be drawing it, it will overlap with this region that represents the probability of A. But let's make sure that we are very theoretically accurate here, okay? P or C. C is a probability. So a probability cannot exceed 1, correct? So I cannot leave this as my answer. My answer must be C. It is supposed to be strictly bigger than 0.2, but C can be less than or equal to 1. Okay, so C is going to be between 0.2 and less than or equal to 1. Next, part 3. We will need the answer that we found in part 1. So let me just rewrite the answer here. Part 1, we have found that probability of A intersects B. This is equal to 0.25. Let's move on to part 3. Part 3, we want to find the probability of A intersects C. And this time, we are actually given another new information, another new piece of information. Probability of C is now 0.45. Let me write it down here. So here, this is equal to 0.45, a new piece of information that is given to me. And we're also given this. We're also given that probability of C given A, this is equal to 0.45. Probability of C given A is probability of C and A divided by the probability of A. So this is equal to 0.45. Probability of C and A is the same as probability of A and C. So this is going to be equal to 0.45 multiplied by the probability of A, and that is 0.8. So probability of A intersects C, this is going to be equal to 0.45 multiplied by 0.8. This is 0.36. Okay, so we have this now, and we want to then state the greatest and the least possible of A prime intersect B intersect C. We have seen this question a few times before in the past few A-level papers. So we want to find the greatest and the least possible of this. Let's get a visual understanding of this A prime intersect B intersect C. So let me try to do a quick sketch of this. Let's say this is A. Let's say here we have here as B, and let's say this is C. So A prime intersect B intersect C is something that must be outside of A, inside of B, and inside C. So it's going to be this region here. So this is probability of A prime intersect B intersect C. What is the greatest and the least possible value for this? So this is how I'm going to be analyzing the question. Okay, I'm going to focus on two things. Number one is I'm going to focus on probability of A intersect C, because we have already calculated this, which means that we know that this region here, it is probability of A intersect C is a constant region. Okay, this region here will have an area of 0.36. So we have this region here, and this is the first thing that I'm going to work on. The second thing that I'm going to work on is the region that is outside, which is actually this region here. Let me mark it down with red color. So it is actually this region here, here. Okay, this is the region that is also fixed, but this is the region that contains this that we are going to be finding. Let me find out what is this region first, okay? This region is A prime intersect C, this red colored region. So what is the probability of A prime intersect C? This is going to be taking probability of C, which we now know it is 0.45, minus away this intersection, which is this. So minus away probability of A intersect C. So it is going to be 0.45 minus away 0.36. This is equal to 0.45 minus 0.36, 0.09. Okay, so we now know that this region here is 0.09. And can you try to imagine together with me, when will this shaded region, which is according to what the question wants, okay, when will this shaded region be the least possible? It will be the least possible if I were to just shift this out more and more away from this B. Okay, we must retain this region. So this region is still 0.36, but we're going to try to shift this out. Okay, we're going to shift this out, which means that if it is actually possible for me to shift this entirely out, then what is the smallest possible for this? 0, right? It's just going to be 0. That means if I can shift until I achieve something that is like this. Let's say here is A, let's say here is B. So if I can shift it until when I achieve something that is like this. Okay, this is C. So this region, which is the intersection between B and C and outside A, there's no such region anymore if I can just shift this entirely out. So if this can happen, then great. The minimum possible is 0. Let's try to see whether this can happen or not. Because in order for us to check whether this can happen or not, we need to look at the amount of space that is outside so that I can shift this out. So the amount of space that is outside, which is this A prime intersect B prime, the amount of space that is outside. Okay, let me just draw it here. Let's say this is A, let's say this is B. So we're going to be looking at this region here. Okay, this is the amount of space that is outside. So this is also easy to calculate. It is just 1 minus probability of A union B. So it's 1 minus 0.95. This is 0.05. Okay, too bad, because there is not enough space to contain this part, this red colored part, which is supposed to be shifted outside. Okay, it is not able to contain, because the region that is outside, this region that is outside, is only 0.05, and this red colored region, which is going to be constantly shifted out, is going to be more, 0.09. But we can definitely shift it out as much as possible. So if I were to shift it out as much as possible, that means we want to make sure that the whole thing is going to be such that this region here is going to occupy everything that is outside. So this region here is going to occupy the entire 0.05. It's going to occupy the entire region that is outside, because when this can happen, then this shaded region is going to be the minimum. So this is how we're going to find the minimum of probability of A prime intersect B intersect C. It is going to be equal to 0.09 minus 0.05, and this is going to be equal to 0.04. Okay, let's discuss when will it be the maximum possible. It will be the maximum possible again if I were to just keep shifting this until when it goes entirely into B. This, I think, it will give us the maximum possible for this shaded region. I'll shift this until this region here goes entirely into this part of B. Okay, which means that I'm going to check whether this is possible. This case. This is, let's say, A. This is, let's say, B. I want to check whether it is possible for me to shift C until when I get this. Okay, where this region is still going to be the region that is outside A and inside B and inside C. Because if I can shift this in, then this will be the maximum possible. So for me to check this, I need to know whether there's enough space here. Enough space that is outside A and inside B for this curve C to be shifted inside. So to do this, I'm going to try to check what is the probability of A prime intersect B. So A prime intersect B is going to be probability of B minus away probability of A intersect B. And this is going to be probability of B is 0.4 minus away probability of A intersect B, which was what we have found in part 1. So minus away 0.25. This is equal to 0.15. And this is possible to contain this region, this red colored region. Okay, because this is bigger than 0.09. Okay, so now we know what is the maximum possible of probability of A prime intersect B intersect C, which is this case, where we try to shift this entire thing inside. So what is this? This is actually the 0.09 that we have calculated, right? This is the space that is outside A and inside B at the same time. So the maximum possible is going to take up just this value. It is 0.09. Okay, this is question number 7. Let's move on. Let's take a look at question number 8. Let's see what we have in this question number 8. Question number 8A. We have this random variable y. Okay, let me write it down. Okay, so for question number 8A, this random variable y, it follows a binomial distribution. It follows a binomial distribution with n and p. These are the two parameters. And the question gave me that the mean is 2.75. So mean of the binomial expansion, the expectation of y, this is n times p, and the question gave me this as 2.75. And we're given another piece of information, which is the probability that y is less than 2 is equal to 0.13122. And we're supposed to find n, we are supposed to find p. So I think from here, I'm going to make n the subject, n is going to be 2.75 divided by p. So if I can do this, then at least we will have less variable to look at. Okay, let me think about it. Okay, I think I will want to make a little bit of change, because expressing in terms of n is actually easier. Then at least I can make use of the table that is in the calculator. So let me re-express and make p the subject. P is going to be equal to 2.75 divided by n. So like what I was saying, then y is going to follow a binomial distribution with n, which is an integer, and p here is going to be 2.75 over n. Okay, working with integer is good. because using the table actually many times it is going to be easier for us to solve for the unknowns instead of working with P, which I think probably I will have no choice but to draw a graph, and I want to avoid graph. So I'm going to make use of this equation that is given to me, which is probability that y is less than 2 is equal to 0.13122 to try to solve for n. So this is the same as probability that y is less than or equal to 1 is equal to 0.13122. So to solve for this, I'm going to make use of my graphing calculator. So on the calculator, second bus, trigger for me distribution. And I'm going to select binomial CDF. So binomial CDF, and the number of trials we are working with n. So here, number of trials, I'm going to put it in as an x. And the probability, we are looking at 2.75 over n. So here, I'm going to put it as 2.75 divided by n, which is going to be represented by x. And the x value here is going to be less than or equal to 1. So here is going to be 1. Let me paste this. Oops, I pasted at the wrong place. Let me redo this again. I should be pasting it here. Okay, so let me just try to do this one more time. So we have binomial CDF. And yep, it is the same parameter here. We're going to paste this inside here. So what I'm going to do is I'm going to generate a table to see what is the value of x that will give me this 0.13122. So let's go for a table, second graph. Okay, let's scroll down this table and see whether we are going to be getting, oh, okay, it is here, 0.13122. So based on the table, we know that if I were to be looking at n, and if I were to be looking at probability that y is less than or equal to 1, when n is equal to 4, this is equal to 0.0935. When n is equal to 5, this is equal to 0.13122. Actually, we can see it from here, right? 0.13122. And when n is equal to 6, this is equal to 0.1535. So therefore, n is equal to 5. And since we know n is equal to 5, p is going to be equal to 2.75 divided by n, which is 5. And this is equal to 0.55. Okay, this is part A of question number 8. Let's move on to part B. Part B, we are looking at a case where there's going to be an average of A% of the residents who are going to be using the bike sharing platform ShareBike. A sample of n residents is taken, and x denote the random variable such that the number of residents will be using this ShareBike. So part 1, state in context 2 assumptions that is needed for x to be well modeled as a binomial distribution. So let me state for you 2. The first one is I'm going to state that the probability of a resident, of a randomly chosen resident, to be using the ShareBike is going to be A out of 100 for every single one of the randomly chosen resident. Okay, so the probability remain constant. This is number 1. Number 2, I will also state that for a resident to be using ShareBike, it is going to be independent of another resident, another randomly chosen resident to be using ShareBike. So 2 conditions. One is constant probability. The second one is all the trials, all the residents who are using the ShareBike must be using them independently of each other. So these 2 conditions, and assuming that these conditions work, I guess. So assuming that x follows a binomial distribution, and n is given to me as 45, a is given to me as 8. Let me try to quote this binomial distribution first. So we are now going to be given this random variable x. We don't even need to define it. So x represents the number of residents who will be using this ShareBike platform. So x here will follow a binomial distribution. A binomial distribution with 45. And here is going to be equal to a over 100 because a is in percent. A is given to me as 8. So 8 over 100, this is going to be equal to 0.08. We are supposed to find the probability such that Okay, this is easy. So part 2, B8, B part 2. So we are supposed to find the probability such that x is at least 9. So x is going to be bigger or equal to 9, and x is supposed to be not more than 13, so less than or equal to 13. To calculate this using my graphing calculator, let me switch back to the question. So it is going to be probability that x is less than or equal to 13 minus away probability that x is less than or equal to 8, correct? Because what we want is when x is equal to, let me write it down, we want to look at x to be 9, 10, 11, 12, 13. So less than or equal to 13 minus away less than or equal to 8 will leave me with a 9, 10, 11, 12, 13. So if I were to press this into the calculator, this will give me my answer to be 0.008432 significant figures. Part 2. And now let's move on to part 3. Part 3, it is given to us that instead n is equal to 12. And the modal number of the residents who use share bike is 2. Modal number, it is the number that caused the probability to be the highest possible. So we know that when the probability of x is equal to 2, okay, it is the highest possible. Use this information to find exactly the range of the values that A can take. Okay, we are supposed to find exactly the range of values that A can take. So I'm going to rewrite x, okay? So x follows a binomial distribution of 12, and instead of a number, I'm going to just go for p. But we know what is p. P here is going to be equal to A over 100. So I'm going to try to find a range of values for p first. Then after that, I'll replace p by A over 100. I think this is less confusing. And since we are given that the model for this model here is 2, so if I were to just imagine how things are going to appear on the probability diagram, for the probability diagram for a binomial distribution, it is going to be of those kind of bar diagram. I think it is called histogram. So we know that when x is equal to 2, it is going to be the highest possible, and which means that towards the left, when x is equal to 1, it is going to be a probability that is less than, and when x is equal to 3, it is going to be a probability that is also going to be less than. Okay, in fact, it will just be less than, less than, less than, less than, and less than, and less than. Okay, it will just be smaller and smaller and smaller. So this is what is going to happen. Of course, we have not finished drawing all the bars that represent the probability for here, but I think this is enough, because in order for 2 to be the model, in order for 2 to be the mode, that means we need to make sure that the probability that x is equal to 1 has to be a probability that is less than the probability that x is equal to 2. And we also want to make sure that the probability when x is equal to 2 is more than the probability that x is equal to 3. This will guarantee us in a more algebraic way, okay, other than just looking at the diagram, this will guarantee for us that 2 is the mode of this distribution. So, and this belongs to a binomial distribution. So quoting this based on the binomial distribution, we are looking at 12 choose 1. P is going to be to the power of 1. Then 1 minus P is going to be to the power of 12 minus 1, so 11. This is going to be 12 choose 2. And P to the power of 2, 1 minus P to the power of 12 minus 2 is 10. And P is a positive number because P represents the probability. 1 minus P, since P is always going to be between 0 to 1, so 1 minus P is also going to be a positive number. So we can actually do some cancellations. 12 choose 1 is 12. Okay, P to the power 1, P to the power 2, this is going to be cancelled. So this will be cancelled. I'm going to be just left with a P here. 1 minus P to the power of 11, 1 minus P to the power of 10, it can be cancelled also without having the inequality sign being affected, because we can be dividing them throughout by P, we can be dividing them throughout by 1 minus P to the power of 10 since they are positive. So we have a 12 multiplied by 1 minus P is less than 12 choose 2, 12 choose 2 from my calculator, this is 66. Multiply by this, we are going to be left with just a P. Rearranging this, we will have P to be bigger than 2 over 13. As for this we have a 12 choose 2. It is actually exactly the same as this. 12 choose 2, 2 to the P to the power of 2 then 1 minus p to the power of 12 minus 2, this is 10. This is bigger than 12 choose 3. Then p to the power of 3, 1 minus p to the power of 12 minus 3, this is 9. So 12 choose 2, 66. P to the power 2, p to the power 3, this can be cancelled. So I'll be left with nothing here. 1 minus p to the power 10, 1 minus p to the power 9, this can be cancelled. So I'm going to be left with a 1 minus p here. 1 minus p here, and this is going to be bigger than 12 choose 3. 12 choose 3 is going to be 220, then p. And rearranging this, we are going to be having p to be less than 3 over 13. So p is bigger than 2 over 13, and p is also less than 3 over 13, which means that, therefore, p is going to be bigger than 2 over 13 and less than 3 over 13. And let's not forget, we are actually not trying to find p, we are trying to find a range of values for this a. So I'm going to replace p by a over 100. So this is going to be 2 over 13. Here is going to be 3 over 13. So the range of values for a is going to be, a is between 200 over 13 and is less than 300 over 13. Have we finished question number 8? Yes, we have. Let's move on. Let's take a look at question number 9. It is a hypothesis testing question. Let's take a look at this question. So this factory supplies beans in small cans. The mass of one can, one randomly chosen can, is going to be denoted by x gram. We are looking at a sample of 40 cans, and the masses were taken and summarized in this summation thing that was given to us. Sorry, let me shift this a little bit. So it is this. Part 1, we are supposed to calculate the unbiased estimate for the population mean and the population variance for the mass of the cans. So part 1 is very standard. The unbiased estimate for the population mean is going to be x bar. So this is going to be summation of x minus 425 over n plus 425. So this is going to be equal to summation of x minus 425 is given to us as minus 136 divided by n. N is 40, a sample size of 40 plus 425. This is equal to 2108 over 5. And we are supposed to find the unbiased estimate to the population variance. So the population variance sigma square is going to be estimated by the unbiased estimate. So it's going to be s square here. And this is going to be 1 over n minus 1 summation of x minus 425 square minus summation of x minus 425 square divided by n. So this is equal to 1 over 40 minus 1. This is 4927.5 minus this is minus 136 square divided by n, which is 40. So this, according to my calculation, this is equal to 114.49, which is going to be approximated as 114 to 3 significant figures. We'll be needing this in the next part of the question, where we are supposed to carry out the hypothesis test at 5% level of significance to check whether the claim of the mean mass of the cans of beans is 425. So we are doing a two-tailed test. Okay, in part 2, we are doing a two-tailed test where I'm going to be letting mu be the population mean. Okay, so let me define mu as the population mean. I'll let mu be the mean mass of a randomly chosen can of bean. Okay, so H0 is we are trying to work on a 425. Mu is equal to 425. mu is equal to 425 because we are supposed to be doing a hypothesis test to check whether it is 425. So it is a two-tailed test. So mu is not equal to 425. The sample size that we are working on, and this is equal to 40, and the sample mean we have already calculated. The exact number is 2108 over 5. And sadly, we do not have the population variance, so we are going to compromise and make use of the unbiased estimate. So the population variance is going to be estimated as 114.49. So this information here will allow me to write down the test statistics. Let me write it down here. And to write down the test statistics in terms of a normal distribution, we find it possible to do so because n, which is given to us as 40, is large enough. So x bar here will follow a normal distribution. A normal distribution with a mean of 4, 2, 5 and a variance of 114.49 over the sample size, which is 40. And this is by the central limit theorem. It is an approximated distribution. And we can definitely write down the standardized version for this also. So the standardized version of this will be x bar minus 425 divided by the square root of 114.49 over 40. This follows a normal distribution of 0, 1. And I'm going to then press this into the calculator directly to get the p-value. So from my graphing calculator, I'm going to obtain the p-value, and that is going to be equal to 0.044466. And we're talking about 5% level of significance. So I'm going to make this conclusion. Since this p-value here is less than 0.05. Since this is less than 0.05, that means there is sufficient evidence. There is sufficient evidence to reject our null hypothesis. So if we can reject our null hypothesis, this implies that the mean mass of a randomly chosen can may not be 4 to 5 gram at 5% level of significance. Okay, this is part 2. And it states giving a reason whether any assumptions about the population is needed for this test to be valid. I guess not. Why not? Because we are looking at n, which is already large, which means that by just making use of the central limit theorem, we can already approximate x bar to follow a normal distribution. We can really approximate the sample mean of a randomly chosen can to be following a normal distribution. So no additional assumption is needed. That will be my answer for part 3. And part 4, can we explain in the context of the question what is the meaning of 5% level of significance? So 5% level of significance here implies that there's going to be a probability of 0.05 that we may conclude that the mean mass is not 425 when in fact it is 425. A probability of 0.05 that through the test we conclude that the mean mass of a can of beans is not 425 when it is actually 425. This is part 4. Let's move on to the last part, part 5. In part 5, we're actually looking at another product. This time we are looking at frozen corn in packets. For its mass, I'm going to use another random variable. We have already used x in the first part, so let's try to go for another one. Let's just use y. So we are going to let y be the mass of a randomly chosen packet of frozen corn. Okay, let me write it down here. So I'm going to let y be the mass of a randomly chosen packet of cons. And I'm going to let mu y be its mean. So according to the question, we are going to be carrying out another test, and this time we are going to be testing against a population mean of 380. The factory claims that the factory claims that the mean mass of the packets of frozen corn is 380. So here, where mu y, this is claimed to be 380. And a packet and 15 samples. Okay, we are working on 15 samples. This is actually pretty small, but the good thing is the question actually told us that the mass follows a normal distribution, so we don't need CLT. Okay, we can really combine these 15 samples of packets of frozen corns together to form a normal distribution. And we are going to be conducting a one-tail test. For these 15 samples, we have gotten a mean of 375. We have discussed this before in our topic outline. The sample mean should always support the alternative hypothesis. So although this question didn't directly tell us, where n, we are given that as 15, and y bar is given to me as 375, which is less than 380. So if the sample mean is always going to be supporting the alternative hypothesis. And according to what the question says, this is a one-tail test. So we're going to be testing that this is less than 380 because 375 is less than 380. And this must always support the alternative hypothesis in order for our hypothesis test to make sense. So this is given. And we are also given the population mean. The population mean, we are given it as 12 square because the standard deviation is 12. So this is going to be equal to 12 square. And based on this, we can once again write down the test statistics. And the test statistics is going to be this y bar that will follow a normal distribution of 380 and a 12 square divided by 15. So we have this. We do not need to write down CLT. We do not need to do any approximation because y already follows a normal distribution. So there's no problem combining linearly multiples of y together. So according to the question, there is insufficient evidence for the rejection to take place. There's insufficient evidence for the rejection to take place. Let's get an overview of what is happening by looking at this scenario where there's insufficient evidence for the rejection to take place on a bell curve. So for my bell curve, the horizontal axis is y bar. Here is 380. And we are looking at a one-tail test, specifically a left-tail test. The level of significance that we're working on is going to be alpha %. So this critical region here, I'm going to let it be alpha over 100. And since there is insufficient evidence, to conclude that it is less than, which means that the sample mean cannot be within the critical region. So it's going to be somewhere here, let's say. So here is 375. So based on this, we know that the probability that y bar is less than 375, this area that is on the left of this, the probability that y bar is less than 375 must be bigger than alpha over 100. And what is the probability that y bar is less than 375? I can just simply press it to the calculator. So making use of this distribution, pressing it into the calculator, for this, my calculator will be giving me this as 0.053292. Okay, this is obtained from pressing it directly into our graphing calculator. This is bigger than alpha over 100. This tells me that alpha is supposed to be less than 5.3292. We are asked to give the set of possible values for alpha. So let's reply in a set notation. So alpha here are real numbers. and it is real number that such that alpha is less than 5.329, so 5.33 to 3 significant figures. But we know that alpha, which is the level of significance, which is in percentage, it shouldn't be negative. So I'm going to just make sure that it is a positive number by restricting it to be bigger than 0. Okay, we are going to move on to our last question. So the last question, let's take a look at it. Question number 10. This is a normal distribution question. So we are looking at a bakery with 2 types of cookies, butter cookies and chocolate cookies. I guess I like both. The masses of the butter cookie is going to follow a normal distribution. It is given to us. And the same goes for the masses of the chocolate cookies. So for butter cookies, I'm going to go for X. So X is given to us as one that follows a normal distribution with 15 and 0.4 square. And for the chocolate cookies, I'm going to go for Y. And this is given to me as a normal distribution with 20 and 1.2 square. Part 1. We want to find the probability such that the mass of a randomly chosen butter cookie is more than 15.5. Okay, this is extremely simple. So for part 1, we are just going to be calculating for the probability the X is bigger than 15.5. Pressing this into the calculator, this is equal to 0.10565, and to 3 significant figures, it is this. And part 2. Part 2, we are now looking at 10 butter cookies, and we want to find the probability that at least 4 of them has a mass that is more than 15.5. This is for one butter cookie. So I'm going to let's say W be the number of butter cookies out of 10 with masses that are more than 15.5 gram each. So W here will follow another binomial distribution with the number of trials 10. The probability of success will be the probability that a butter cookie weighs more than 50.5 grams. So this probability here is going to be 0.10565. So this space is for this. And we are supposed to be calculating that there are going to be at least 4 of the butter cookies that are going to be weighing more than 15.5 grams. So this is at least 4. And to calculate this using our calculator, we're going to rewrite this as 1 minus probability that W is less than or equal to 3. And pressing this into the calculator, the probability is 0.0155. And now we are going to be looking at the price that we are going to be paying for the butter cookies. For the butter cookies, it is going to be $6 per 100 grams. So let me write it down. So this is going to be 6 per 100 gram. And for the chocolate cookies, it is going to be $7.50 per 100 grams. Let me erase this. So we are going to be looking at Miss Lee, who has bought 12 butter cookies and 12 chocolate cookies, and we want to find the probability such that she is going to be paying less than $29. So I'm going to let S, or I'm going to let the total cost. Okay, I'm going to let T. Okay, T is already used in the next part. Okay, let me just go for S, the sum of the price. Okay, so I'm going to let S be the sum of the cost of 12 butter cookies and 12 chocolate cookies. So for the cost of the butter cookie, this is in grams, 1 gram. Okay, I mean this is in grams, and but the price is given to us as $6 per 100 grams. So for 1 gram, it is going to be 6/100, and we're talking about 12 butter cookies. So x1 plus x2 plus x3 all the way until x12, and the same goes for this. This is for 100 grams. So for 1 gram, it is going to be this. And we're looking at 12 chocolate cookies. So y1 plus y2 plus y3 all the way until y12. So I'm going to try to find the expectation of the sum of the money that Miss Lee is going to be paying. And it is the expectation of this, which is going to be 6/100. And here we are going to be looking at 12 instances of x. So it's 12 times the expectation of x. Plus, same goes for this, 750/100, and 12 times the expectation for y. So this is going to be equal to 6/100, and 12 multiplied by the expectation of x is 15. Then plus 750 divided by 100, 12 times of the expectation of y, which is 20. And this is going to give us an expectation of 28.8. We're going to find the variance also. So similarly, the variance of S, this is going to be equal to variance of this. We'll have a 6/100 square for variance. So it'll be constant square. Then we will have a variance of 12 different instances of x. So it's going to be 12 times of variance of x, and the variance of x is 0.4. So we have a 0.4 square plus this, which will give us this over 100 square, and 12 of this, so it's going to be 12 times of the variance of y, which is 1.2 square. And this will give us the variance as 0.104112. So the sum is going to follow a normal distribution. A normal distribution with the mean as 28.8, and the variance is 0.104112. And we are supposed to calculate for the probability that the total sum that Miss Lee is paying is less than $29, less than 29. So we just need to press it into our calculator to find this normal distribution. This is equal to 0.732. And do we need to make any assumption in order for this calculation to be valid? Yes, we do, because the question didn't mention this to us. So we are going to try to assume that the mass of all the cookies that we are looking at, they are independent of each other. Okay, please take note, we cannot just simply say that the mass of the butter cookie is independent to the mass of the chocolate cookie. Because we are not trying to just sum one butter cookie and one chocolate cookie. We are trying to sum all the cookies together. So even within here, the butter cookies must be independent of each other. Same goes for the chocolate cookies. And definitely for the butter and chocolate cookies, they must also be independent of each other. So for this part here, for part 4, do we need to make any assumption? Yes, we need. So let me repeat again. We need to assume that the mass of all the cookies are independent of each other. All the cookies, including, which means that the butter cookies and the chocolate cookies, all of them, the masses must be independent of each other. And now we are looking at another distribution. We are going to be looking at the distribution for the time that is taken for the customer to be served at the bakery. We are given the mean and the variance for the time. So we are given the expectation for t and the variance for t. The expectation for t, this is given to me as 16. And the variance for t, this is given to me as 9 square. The standard deviation is 9. So the variance is going to be 9 square. Part 5. Can we give a reason why a normal distribution with this mean and with this variance or with this standard deviation would not be a good approximation to the distribution for t. So we are trying to check that it is not a normal distribution, and I think one of the best and easiest way for us to produce a solution for this is to make use of a counter example. What do I mean by a counter example? We need to first imagine a scenario where the probability is already known. Okay, this is regardless of whether it is a normal distribution or not. For example, t is the time that is taken for the customer to be served. So we know that it is impossible for t to be a negative number. It is time for the customer to be served. So it cannot be negative, which means that if we were to calculate the probability for t to be less than 0, we will be expecting the answer to be 0, right? Because it is impossible for the time to be negative. So let's try to make use of this as our counter example, and we will verify this by first assuming, okay, we don't know whether it's a normal distribution, but we are going to be assuming. We are going to assume t as one that follows a normal distribution with a mean of 16 and a variance of 9 square. And then we're going to make use of this following a normal distribution to calculate the probability for t to be less than 0 using the normal distribution. And if you were to press this into the calculator will give you this 0.03772. And and look at this. Okay, well, what are we expecting? We're expecting that the probability is 0 because this shouldn't happen. But this is telling me that it is going to happen like approximately 4 out of 100 times. That means if 100 customers come in, 4 of them are going to be experiencing a negative time when the person is going to be served. Okay, this is not possible. So we are looking at something that is not even negligible. It is still significant. So if t follows a normal distribution, it is not able to produce us a satisfactory answer. Therefore, based on this as a counterexample, we conclude that t will not be one that follows a normal distribution, or a normal distribution will not give a good approximation for the distribution for t. Then the last part 5, the waiting times for n randomly chosen customer is taken, and n is a number that is bigger than 30. We are given that the probability for the average waiting time is we are given that the average waiting time for this n customers that is between 16 minutes and 18 minutes is more than 0.48. We are supposed to find the least possible value for n. And now the scenario has changed, because instead of working on just t, we are looking at a combination of n numbers of t, and n is bigger than 30. So since n is bigger than 30, which we will consider as large. That means when I try to find the average of n numbers of times the customers is being served, we are looking at t1 plus t2 plus all the way until tn divided by n. We are looking at this, the average, when the average time for n number of customers to be served. So this is going to be t bar. And t bar will follow a normal distribution with mean as 16, and its variance is going to be 9 squared divided by the sample size. In this case, it is n, and this is by the central limit theorem. We are doing an approximation here because n happened to be large. And we are given this. We are given that the probability when t bar is between 16 and 18, this is bigger than 0.48. So we are given this inequality, and we are going to make use of this inequality to find the least value for n. And in order for us to make use of this inequality and to find n, I think one of the possible way is for me to try to break down this inequality, or break down the notation that is given to me for probability, so that I can use my graphing calculator. I mean, now I cannot do so because of the n that is here. So I'm going to try to do a quick imagination for this, okay? I'm going to go back to the bell curve again. It is good for us to develop the habit of always referring back to the bell curve when we are working on a normal distribution, and we need a little bit more visualization, okay, because calculation is not going to instantly work. So whenever it is this case, and if we are sort of stuck, let's just go back to our graphing, to our bell curve. And on this bell curve, the horizontal axis is t bar. The center here is going to be equal to 16. And the question says that the area that is between 16 to 18, 18 is going to be here. 16 is actually the mean. Okay, so this area here is going to be bigger than 0.48, which means that I can re-express this area. Okay, just based on area, I can now re-express this as probability that T bar is less than 18, which is this entire area here, minus away probability that T bar is less than 16. Okay, this will help me to re-express the left-hand side. T bar is less than 18, minus away T bar is less than 16, it's still going to be this area, and this area is bigger than 0.48. And this is probability that T bar is less than 18. And what is this? This is just half of the area that is here, because 16 is the mean. And the bell curve is going to be symmetrical about the mean. So this is going to be 0.5, this is bigger than 0.48, which means that probability of T bar is less than this. This is bigger than 0.98. We are going to try to solve for n. And in order for us to press it into our calculator, we are going to standardize the left-hand side. So on the left-hand side, we will have a z is less than 18 minus 16 divided by square root of 9 square over n. This is bigger than 0.98. So the probability of z to be less than, this is 2 square root of 9 over square root of n over 9. This is bigger than 0.98. This is something that we cannot press directly into the calculator to get this. Okay, so we need to have a little tweak, we need to have a workaround. So the workaround will be this. The workaround will be simulating something that is like this, but going for an equal sign here. Okay, because of this is the reason why we cannot press it directly into the calculator. So I'm going to just look at this probability that z is less than 2, instead of 2 square root of n over 9, I'm going to write this as less than, let's say, a. Okay, and I'm going to let this be equal to 0.98. Okay, this scenario here allows me to press it into the calculator. I can just press into the calculator for inverse norm, and the calculator will give me this value to be equal to 2.0537. Okay, let me just rewrite this. So this is going to be 2.0537. Okay, why am I doing this? Okay, again, we are getting a little bit stuck in terms of our calculation for the normal distribution. So let's go back to the bell curve. Going back to the bell curve, this is what we have gotten. I'm going to be basing it on z. So here is going to be equal to 0. And we found that when it is 2.0537, this area here is 0.98. That is what that is implied in this statement here. And for this, the area that is on the left-hand side of this number is bigger than 0.98. So what do you think is this number? I repeat again, the probability that z is less than this number is bigger than 0.98. This implies that this number must be on the right of 2.0537, correct? Because the area that is on the left is equal to 0.98. So something that is on the right of 2.0537 is going to give me an area that is bigger than 0.98. So I'm assuming that 2 square root of n divided by n is going to be on the right hand side of 2.0537, which means that from here we can then conclude that 2 square root of n over 9 must be bigger than 2.0537, and then making n as the only term that is on the left hand side, I will be getting n to be bigger than 85.412, and therefore from here we will be able to find the least possible value of n. Since n is bigger than 85.4, the least possible value of n is an integer value. The least possible value of n is 86. And this concludes for us the section B of this VJC 2021. And I think quite a few of you are going to be having your A-level this week. So I wish you guys all the best for your paper 2, and hopefully with a little bit of practice together with me, you will score even better for your paper 2.